It's Mr. Van Dong here with week 5, day 2 of your distance learning. We're doing math. We're going to use these cool things called protractors today. So we're on page 909, and we're going to be doing lesson 2 of chapter 12. We're looking at the sides and angles of triangles. So we're doing our first deep dive into triangles, which are three-sided polygons. And today we are going to measure the length of their sides and measure their interior angles using this cool tool. Some of you might have used a protractor before. A lot of you will have not have done so, and that's okay. We're going to go over in detail how to use one of these bad mamma jammas, which should have been sent home in your packet, by the way. And on them, they also have rulers. These need to be sent back at the end of the chapter. You don't have to send it back this week. Please keep it because you'll need it like for the little assessment at the end to kind of see what you know how to do and what you don't know how to do yet. And for other assignments, you'll need it too. But they are classroom supplies for the school, so please do send them back when we're all the way done with chapter 12. Okay, let's get started on the assignment here. So there's 6 triangles, and they want us to measure to the nearest centimeter the length of every side. So let's do that. So this is going to be kind of weird. I'm going to actually like use the book and do things and hold it up here and use the whiteboard a little bit less, but that's life. So here's a thing to notice immediately about protractors. Protractors tend to be a lot more useful if they're clear. And you'll kind of see why once we're using them. But that also means that you can hold them in such a way where all the numbers appear backwards. So the first thing that you need to do when you're using this as a measurement tool, well, if I put it like this, it'll be over my mouth. Some of you will appreciate that. Is to make sure that when you're looking at it, that the numbers are written left to right, like normal. Okay, so our right here we have our metric ruler, and every number that you see there is 1 centimeter. The mm means the little tiny hash marks are millimeters, and these are the centimeters here. So let's get to measuring. So on that first triangle there, if I measure one of its sides by carefully putting it up to the 0 like this, I can see that it is exactly 3 centimeters. Go ahead and measure the other ones, and you'll notice that they're also all 3 centimeters. Okay, so we've got our first triangle. All of those are 3 centimeters. Let's measure the next one. Again, I hold that up carefully like so, lining it up. Oh, it's 2 centimeters exactly. Okay. And spoiler alert, when you measure those other ones, go ahead and measure them now. See, hey, you can kind of look and see those all look the same. And then your measuring tool will tell you, yes, they are the same. So those are all 2 centimeters. All right, let's do the next pair. I'm going to begin by measuring the bottom of this one. Notice that it's important that I try to lay this flat. If my book is kind of bent like that, it won't be accurate. So it froze when I did that. I need to try to actually lay it flat as I can on my page. So that appears to be almost exactly 3.5 centimeters, which is the devil because they told us to round to the nearest centimeter. So 3.5, I guess we'll round up to 4. We're going to follow their directions. So, it says nearest tenth. Mr. Van Dong, did you notice that it says the nearest tenth of a centimeter? Of course, I was testing you. Of course I knew. Of course I knew that was there. So nearest tenth of a centimeter. A tenth of a centimeter is a millimeter, so we should just be measuring to the nearest millimeter. But in any case, if we remeasure that, it's 3.5 centimeters, 3.5 centimeters. It'd be 35 millimeters. We're going to write 3.5. So we're counting each of those hash marks is 1/10 of a centimeter. So if we count the hash marks in between 3 and 4, we went up 5 to get there. Okay. Glad you noticed that imaginary student in my head. So we measure the next part, and it looks like it's exactly 2. And if we measure this other angle, that also is exactly 2. Okay, so we've got a 2 centimeter, 2 centimeter, and 3.5 centimeter measurement here. All right, next is this bad mamma jamma. If I measure that bottom one, it looks like it's exactly 2. And then the other part that connects to that right angle, that red symbol is showing that it's a square angle, or more accurately called a right angle. You can call it either. That vertical line segment there is also 2. centimeters. And then the hypotenuse, which is a word that you'll learn one day, but not right now, is 3 centimeters. Okay, so we've got 2 centimeters, 2 centimeters, and 3 centimeters. Okay, cool. Next, this one down here, the first one in pair C, I see that looks like it looks like it's 2.5. You might call that 2.6, and that's close enough. I'm going to call it 2.5 based on my measurement right there. And then I'm going to measure the shortest one, that more vertical one. Why am I measuring that one first? Because I feel like it. It doesn't matter the order you do it. Looks like it's 1.5 centimeters right there. And then the longest angle here looks like it's 3.5 centimeters, 3.5 centimeters. Okay. All right, let's do the last one. That is going to be 3. This one is going to be 2. And this one is going to be, that's hard. So I'm going to write these ones down before I forget it. 3, 2. It's going to be like, I bet a lot of you were hoping it would be 4, but that's not how it works. 3.6. 3.6. It's somewhere between 3.6 and 3.7 based on my measurement. If you said 3.5, you're not being as accurate as you should be. Okay, yay, we measured the sides. We've measured the length. Let's imagine that we're talking about it for the next problem. So it says compare the triangles above. So see how they paired them? In pair A, all of them, they always made it so that the sides were equal. So these were both regular triangles. And then in pair B, they made it so 2 of the sides were equal, and one of them was a bit longer in this particular case. They could have made it so it was a bit shorter. I wish they would have done one example where it was shorter, but it doesn't matter. In any case, 2 of the sides are equal, and one of them is not. Should I be saying equal or should I be saying congruent? I should be saying congruent. And then for pair C, none of the sides are congruent. They're drawing your attention to that because tomorrow we're going to begin. Wait, am I lying? I don't think I'm lying. Let me make sure I'm not lying. Not lying. Tomorrow we're going to begin classifying triangles. And one of the criteria we classify triangles based on is the number of sides in that triangle that are congruent. And there's a fancy word for whether there's all the sides congruent, 2 of the sides congruent, or none of the sides congruent. So that's why they're drawing your attention to that. All right, let's talk about the angles. Go ahead and turn the page. And we're going to use your protractor. It's here. It says measure the angles of each pair of triangles below to the nearest degree, then record the measurement. All right. Math might go a little bit long today because of this explanation of the protractor. So FYI, if you're like, Mr. Van Dung, this video was super long, I didn't have enough time to practice. Like, practice more. This is important. This is part of a circle. If I had 2 of these, I could make a full circle. And degrees are the measurement tool that we use to talk about how much something has rotated in part of a circle. So I'm going to use my arms for a second. So see, it's like I'm turning part of a circle, right? Maybe I should use this tool here to show that instead. So I could turn in a full circle. And everybody knows going in a full circle is a 360. All right, that's that move in skateboarding, rollerblading, skiing, snowboarding, it's diving. It's called a 360 because you go 360 degrees. Mr. Van Dung, why did they make it 360 degrees in a full circle? I get asked that question every year. I look it up every year, and then I promptly forget it every year. I have a hard time remembering that factoid. So I don't remember. With parent permission, you can look it up. Why are there 360 degrees in a circle? I don't know, because that's the way we do it. I hate saying that, but I'm not going to look it up right now because it's going to take long enough as it is. So 360 degrees is a full rotation. That means half of 360 is 180. Half of 360 is 180. So going around halfway is a 180. Notice that on our protractor, our measurement tool goes to 180. Mr. Van Dung, I noticed it says 180 on both sides. Well, it actually doesn't, but anyway, it could. Yeah, so about that, we're going to talk about that. There are 2 sets of numbers as we go around here, okay? And you can use either. The important thing when we get to actually measuring with this is that you always start at 0 and then measure the amount of turn. Did you hear me say amount of turn? I hope you did, because the amount of turn is how we want to define an angle. So an angle is the amount of turn there is basically between two lines. Okay, so it's the amount of turn there is. All right, so here's another kind of weird thing about measuring in degrees. So again, we measure this in degrees. Degrees are not a distance. Let me show you what I mean. Degrees are not a distance. They're an amount of turn. I want you to imagine that there was an angle that looked something like this. Okay, I've drawn, I'll just tell you that this amount of turn right here is about 45 degrees. It's probably, it looks closer to 50 as I estimate it, but let me measure it to check. I know I haven't taught you how to do this. It's okay. No, it's 45 exactly. Whew, nice job, Mr. Van Dam. So we draw this part right here. This is literally part of a circle where the center of the circle, look, I drew Pac-Man, where the center of the circle is where the two line segments meet. So the reason why we draw that is we're drawing part of a circle saying this is the amount of turn there is. So we draw that there. Now, I could draw the amount of circle there or out here. It doesn't matter. Each of those, that is 45, and the symbol looks like that, 45 degrees of a turn. If I were to measure, if I were to put points on my line segments, let's pretend that I put a point here and called it A, and a point here and called it B, and a point here and called it C, and a point here and called it D. If I were to measure, let's pretend that this was like a giant windmill and we were strapped to it. It was like a really fun fair ride where you get strapped to a windmill and tumbled around. Okay, if I'm strapped here and the blade turns, I would travel through the air, a certain distance. Let's pretend that these were, we'll just measure centimeters. I got shrunk down. Anyway, like the distance, the straight line distance between A and B here is like 40 centimeters. And the straight line distance here between C and D is like 11 centimeters. We're not measuring straight line distance though. This is from A to B or from C to D. It is 45 degrees. The amount of turn is the same, is 45 degrees. The distance you travel if you were strapped to the blade of a windmill would depend on how close you were to the center of the windmill. And this is how a lot of fair rides work, by the way, if you've ever been like on the Gravitron. All fair rides are just different versions of circles spinning. That's all they are. Circle in the air, circle sideways, circle flat on the ground. How fast do you spin the circle? Circle spinning in a circle. They're all circles. If you're on the Gravitron, if you are, there's a person operating the ride in the exact center. And they don't get dizzy and they don't feel like they're being thrown out to the edge of the room or anything like that. And the reason why is because they're not moving at all, other than they're turning in a 360-degree circle, but they're not actually moving through space, like through a distance, right? Whereas if you're out here on the Gravitron, your 360-degree circle sends you all around the ride in a greater distance, and so there's more force. So now we're kind of getting into physics, and I've gotten distracted because it's fun to talk about these things, and I hope you're interested in them too. This is sort of where math and physics start, really meeting together, is with geometry. And so that when we're talking about degrees, specifically in 5th grade, I want to make sure you understand we're not talking about a distance, we're talking about an amount of turn. An amount of turn. Okay, let's try it. Let's try to measure the amount of turn. What you need to do anytime that you are measuring with a protractor, that protractor always has a little target, like a sight, okay? And this one looks right, it's right there. You need to put your sight on the point where the line segments intersect. So if we're going to measure this first one, I need to put my little target on right there. See how I've put it right where they're meeting? And then I can twist the protractor like this, keeping that sight line focused in where the line segments meet. Now what I want to do is I want to twist this so that one of the lines perfectly lines up with the flat edge, the straight line on my protractor. See how if I go like this, you can see the blue line there? Totally cover up that bottom blue line with the black part of the protractor. That's why it's see-through, okay? Now to know the amount of turn, I need to know where this line would hit the ruler. And I can just kind of see it on this one, but you can see it's kind of a problem using a protractor that is larger than the object, than the shape that you're measuring, can be difficult. So if I wanted to be really, really accurate, the first thing I would do before measuring is I would actually go ahead and extend a line right here further up to make sure that I can measure it. So I just put my straight edge there and I just go like that. Okay, now when I measure with my protractor, I can actually see where that line goes. So I'm going to line up that exact same measurement again. And now where does the black line go? It goes to the 90. Mr. Van Dong, there's 2 90s. Yes. Think carefully about the direction of turn we're measuring. Right now, we're starting, our baseline is 0. So if we follow that, that's the 0. As we turn in this direction, in this particular case, I'm measuring counterclockwise turn, the opposite direction that a clock moves. I need to find the numbers that are going up as I move counterclockwise. The interior numbers go 10, 20, 30, 40, 50, and so on as I go up. So when I'm measuring counterclockwise, I track these numbers that are on the inside of my protractor. These numbers start at 180 and they're getting smaller, and that doesn't make sense to use. I'm going with a little turn to larger and larger numbers. So where does that point to? It points to 90. It goes right at the 90. So how many degrees is that angle? It's 90, and then do the degree symbol. Go ahead and practice writing the degree symbol so it's clear. 90 degrees. That's a right angle. That's a square angle, okay? Let's measure another one, okay? Again, I'm gonna kind of think ahead. So what you don't want to twist, I don't recommend twisting your protractor like this to do a measurement. Don't hold your protractor upside down, you're gonna make a mistake. Turn your book upside down. Keep the protractor in this position all the time and twist the paper. So I'm gonna twist this paper like this time so that I can measure this next angle. So I've got the book upside down and I'm ready to measure that angle. So I've got it lined up and I'm intentionally showing you on this one. Now the amount of turn I'm going to measure is going to go clockwise, right? So I'm measuring to this line right here, but I can't see where it goes. So just like before, I need to extend that line. So your final work product today ends up looking kind of strange and ugly because you're going to need to do this a lot. Extend the lines out. You have pencil, right? I'm using a pen, so it's really easy to see on camera. You should use a pencil and do it really lightly so you can still see everything else and it's not too confusing. But in any case, okay, I'm going to line that up again. Okay, and where does my line go? it looks like it goes to 60. It actually kind of looks like 61, but I think I didn't draw a line super accurate. Just like before, if you're within like plus or minus 2 or 3 degrees, it's right. Okay, it doesn't have to be perfect. Try to get within plus or minus 2 degrees. I think it's supposed to be 60, so I'm gonna write 60. Okay, so it's a 60-degree angle right there, and I don't have to measure the last one. Do you want to know why? The interior angles, the inside angles of every triangle, they always add up to 180, to half of a circle, 100% of the time. It's a rule. It's a universal law of triangles. Because of that, I could go, ooh, 90 plus 60 is 150. That means that this has to be 30 degrees. I'll show that, Mr. Van Dog. I'm not even going to measure that one. If you want to do that, that's fine with me. Now, I'm still going to double check and make sure it looks like it's about 30 because I don't want to screw it up. So I measure that last angle there, and does it look like it would go out to the 30? It sure does looks like it will go out to the 30. Wait, it looks like it would go to 150. Yeah, it does look like it would go to 150. Remember, you have to be careful which set of numbers you're looking at. Look at the numbers that are increasing with your amount of turn. You also can just sort of estimate and be like, does this little angle, does this amount of turn, does that look like it's going to be less than 90 degrees or more than 90 degrees? It's going to be less than 90 degrees. So look at the number that's less than 90 degrees. Okay, I'm already 21 minutes in, so I'm going to stop pretty much. I want you to finish measuring these on your own individually, and then you're going to do the same thing as before. Do the talk about it section. You're looking for patterns about how many of the angles are congruent, because that's the other factor for classifying triangles. So finish these protractor measurements. If it's really normal for kids to be like, I still don't understand a protractor. Okay, again, if you're watching this video, you have access to the internet. So with your parents' permission, Google how to use a protractor and watch other videos about how to use this to make sure that you're proficient at using a protractor. Okay, totally fine to do. Information and knowledge is out there. Go get it. Okay. Maybe work a little bit longer on today's. If you don't finish in 45 minutes, but you've like barely even broken into this page, I would keep going. I would work for up to 60 minutes today, probably, or maybe skip your math choice time if that's something that's available to you, and just work on this because it is important. So that's my suggestion to you. But you do you is the bottom line. Make sure that you feel good about measuring the sides and angles of triangles. Catch you tomorrow.